We're going to take a look at the number system in section 4 of chapter 3. Make sure that you've watched the previous lectures so that this makes sense to you. And we're going to be talking about addition and subtraction algorithms, mental math, as well as estimation. So we want to be able to develop models for algorithms for addition and subtraction to really scaffold that thinking from simple arithmetic to allowing them to understand algebra. And we're going to have algorithms that include the standard algorithms and how to use them to solve problems. We're going to look at number bases other than 10 to give us some insight into base 10 algorithms. And we're going to look at some mental addition and subtraction skills and estimation techniques. So a concrete model is what's referred to a lot on social media and by parents as traditional addition. So I write my addition statement in two columns. I'm going to add one column, add the other column, and carry anything in between. This is kind of a concrete model. One of the ways if you're teaching this model to students is you can actually have them use manipulatives, and then you're able to take two separate groups of manipulatives and bring it down into that summation. And we want them, of course, to use tens and group the tens together so they can see 10, 20, 30. And then we have the 1. So that's one option. We can also expand this idea into trying to move to a 10. So if I look at 14 plus 23, if I add 7 to 23, that gives me 30. So you can think of it as if I borrowed 7 from 14, this new arithmetic statement becomes 7 plus 30, which is 37. This is kind of related to one of the other strategies we already talked about before, in where we're trying to get things into groups of tens so that they add easier. And this, I mean, at first glance, it seems like, well, this is just much more complicated than I want to teach students. But as we move into the concept of borrowing and subtraction, this is laying the foundation for that. So it's just basically trying to regroup the numbers by tens so that you can add easier. So here's another example of the expanded algorithm with what we're calling regrouping. So I have 28 plus 37. I know that if I borrow 2 from that 37, that gives me 30. But why not borrow 22 so that I get 15 plus 30? So different ways of regrouping these statements to making them easier to solve. Obviously, again, it's recognizable that those columns add quickly together and you could carry, but by regrouping, we're teaching the principles of borrowing. For subtraction, we're also teaching principles of factorization that's going to be built upon for algebra. So there's a lot of foundational concepts where it benefits students from seeing this method. So if I want to look at this, we could add the ones, regroup, and then add the tens traditionally. That would be the standard algorithm, not the expanded algorithm. If I want to move to 3-digit numbers, I'm going to do some of the same thing here with 3-digit numbers, but I could maybe move it to 200 if I was trying to use an expanded algorithm by regrouping things. Or I could potentially look at 6 ones plus 7 ones is 13. So I could borrow a 10 and move that way where I'm regrouping by 10. So if I add the tens there, I can start working on, I have 1 10 plus 8 tens plus 2 tens would be 11 tens. So if I'm looking at those 11 tens, that will give me a 100 plus 110. Now, again, is this a strategy we want students to do every single time they add? No. But again, we're laying the foundation with this whole idea of regrouping. So we talk about borrowing from the hundreds place. We understand what we're borrowing from, and we can quantify what that borrow means. So here we're teaching them that 11 tens is 100 and 110. So we're quantifying the borrowing process that's happening. Then we can work on adding the hundreds together, and we can get our final answer of 313. I could also use a left to right algorithm. Sometimes we would be able to say, okay, well, 568 plus 757, I could break that down into place value. So 500 plus 700, 60 plus 50, and 8 plus 7. This is place value. So 568 is 500 plus 60 plus 8. And what I'm doing is taking that concept of place value that you may have thought, well, why am I even teaching this, as a addition strategy. It is easier to move if I'm looking at addition from this perspective. The lattice algorithm for addition is basically looking at the ways that we can group numbers. So I have ones and tens. So 3 plus 5 is 3 eighths and 0 tens. 5 plus 6 is 1 in the 1 place and a 1 in the tens place. So I'm kind of working towards carrying things over when I'm doing the lattice method. Again, this is probably not going to help the large portion of your learners, but you might have some small students, groupings of students that like this. A scratch algorithm would be add the number in the ones place, starting at the top, and when the sum is 10 or more, you record that by scratching and putting the remainder there. So 7 plus 5 is 12. So that scratch mark is reminding me that I have a 10 and I'm putting a 2 there. And I would do 2 plus 9 and I would work from there. And I would say, well, 2 plus 9 is 11. So I'm scratching 9 and putting the 1. And then from there, I know that I have 2 scratches in the units place. So I'm carrying 2 into the tens place. And then I can do the same method with the scratching there. And I would have students use a different color because 8 plus 2 is 10. I'm going to scratch and put the 0 because 10 is 1, 0. Plus 6, we're good. 6 plus 4 is 10, so I'm scratching, putting a 0. And then I have 2 scratches in the tens column, which makes it 201. But again, I like using different colors in the columns with this for students. And this is perhaps for students that make common mistakes with carrying. So if they're forgetting to carry values over in that vertical addition, this might be a positive strategy for those groups. Subtraction algorithms are similar. We have our concrete model, 2 columns. We're borrowing like normal. This is exactly the math that we learned when we were growing up, most likely. This is the math that all of the parents want to talk about. And then we can start talking about taking away. And the nice thing is when we're working with the blocks, we can really teach students that when I break apart 100, that's going to give me the 10 tens, and then I can replace and borrow. So this is kind of the traditional hands-on method when I'm teaching that basic concept to students. The subtraction algorithm is going to be a concrete model again. And so this is just using that concrete model and getting our final answer of 100 because I have 100, 8 tens, and 2 ones. If I have the equal add-ins algorithm, so I'm going to basically be working towards getting those whole and even numbers here so that I'm adding a little bit easier. This is based on the fact that the difference between 2 numbers doesn't change if we add the same thing to both numbers. So if I add 7 to 163, that's going to give me 170, which is a little bit easier to work with. And then if I add 30 to both, again, that puts me at 292 minus 200. So it's easier. This is a really nice foundation and groundwork for equations and solving equations, but it's not what you want to show your students when you first embark on subtraction. This is an extension activity for students that are really grasping that subtraction. Some additional ways that we look at this is we have bases other than 10. I can work with things and I can have 343 base 5 plus 2 base 5 equals 400 in base 5. And then at the bottom, I have the same thing with the subtraction. So the question is, where is this coming from? Well, I can look at the concrete model and say that 12 in base 5 would be, so in the tens place, we have a 1, but because we're base 5, that gives us 5. We have 2 in the units digit, so I have 2. So the 12 in base 5 is really 7 for what we know. 31 base 5, there's a 3 in the what we would call the tens place, so there's 3 groups of 5. 1 group of ones. And so I'm adding these together and I have 1, 2, 3, 4 groups of the tens place. So I have 4 and 3 unit places. So this is really tough to do, guys, without drawing it out. I really, really encourage drawing it out because sometimes when we're looking at larger numbers, it's not as easy as straight up adding the things one to the other, such as we saw here with 343 plus 2 is 400, not 345. So it's definitely worth sketching this out so you can fully understand it. So if I'm looking at the expanded algorithm, I have 2 plus 1 is 3. And then I have 3 plus 1, it would be the 4. So I'd have 4 groups of 5. So it would be 43. That's kind of nice. If you notice when you're doing addition in base 5 with numbers less than 5, then it's just kind of straight addition. It's when we have something greater than 5 that we start running into problems. Here are some more examples. If I have, looking at base 5, 32 in base 5 isn't really 32. It's 3 groups of 5 and 2 units. If I want to take away 14 in base 5, that's 1 group of 5 and 4 units, so that I'm left with 1 group of 5, and I have 3 left because I had to borrow from this upright group. So that's kind of leaving behind those processes that might be a little bit more strenuous for you. And we're just going to take a look at mental math and computation estimation. Mental math is something that we want students to eventually approach. We want them to be able to add numbers like 76 and 25 to themselves. So if I look at 76 and 25, I'm going to do 70 plus 20. That's how I actually add. And then I do 6 plus 5, and I add those together in my head. So when we're looking at adding from the left, we're really kind of talking about almost like rounding it off to a lower number, or we're looking at that place value idea that 76 is 70 plus 6. 25 is 20 plus 5. Another way is we could break it up in bridge. So we can actually take the 25 and make it 20, because 76 plus 20 is 96. That's not too tough to do. And then I just have to add that last 5 that was hanging out there. Trading off is another strategy where we can say, well, I have 76 and 25. So if I take 4 away from that 25, that puts me at a nice even number of 80. So that I have to add 80 plus 21, not 25, because I have to account the fact that I borrowed it. If I'm looking at compatible numbers, that's just whole rounded numbers like 200, 150, 60, anything that's easier to add. And that's why we like teaching students place values, so that in an expanded form of numbers, so they can really break this down and add easier in their minds. So if I have 76 and 25, well, 75 is a pretty easy number, and so is 25. When I'm adding them together, that's 100. And then I just have the 1 left over because it was 76. So it doesn't have to end in a 0 to be easy. Here's a couple of examples of how this is done. You can drop off the zeros and add them on at the end in 3, but there's additional examples of bridging and trading off in this slide. Here's an example of a word problem. If Noah owed $11 for his groceries and he used a $50 bill to pay, while handing Noah the change, the cashier said 11, 12, 13, 14, and 15, 20, 30, 50. How much change did he get? So we can break this down into looking at, well, if you went from 11 to 12, that's 1. 12 to 13, that's a 1. 13 to 14, that's a 1. Again, then 15 to 20 is $5. 20 to 30 is $10, and 30 to 50 is 20. So making a table for those kind of problems is going to be the easiest. Then you're actually going to check the change to see the amount of change that he got. And to find the original price, we know that he paid $50. So if I subtract the change from the $50, I get the cost of the item. So a computational estimation method would be adding front end digits. I'm adding what's in the front, and I get 11. So which that would be, it's 11 100, so it'd be 1100. And then I can adjust 22 plus 31 is 50, approximately 50. 74 is approximately 70. So I'm just estimating. And I tell students, it's really hard because in math, when they get older, we don't really want them to estimate a whole lot. We want exact answers. But if I'm in the store trying to figure out if I have enough money to buy something, I'm going to use estimation. So this is a valuable skill that we need our students to learn. And I tell my students, it's kind of like rounding. When you're looking at estimation, you're just kind of trying to round up or down to those nice ending in 0 numbers. We can also look at grouping what we call nice numbers, which are going to be numbers that, again, end in those zeros. So if I'm looking at adding 5 or 6 things together in a vertical column, instead of trying to add all of the ones and all of that, to get a little bit quicker mentally, I could do grouping them together to get those nice numbers. I can also use clustering. Clustering happens when I'm adding numbers that are kind of clustered around one central number. And if you look at all of these values, they're kind of clustered around 5,000. So I could do 5 times 5,000 to get an estimate of 25,000 much quicker than I could actually do the vertical addition. And then rounding is a subset of estimation. So I would be able to round to the nearest digit that is going to end in zeros. And I would know that if I'm rounding down, it's a low estimate. If I'm rounding up, it's a high estimate.